People have known for a long time that planning ahead is both important and difficult. With mounting evidence of the scope and intensity of rapid climate change, the imperatives of planning for a future that will be unlike the recorded past have grown dramatically. As a consequence, it's important that researchers develop not only better means to communicate climate science, but also better tools to engage people from all walks of life in planning for their collective futures. Alternative futures analysis is an established approach for achieving both these ends and more. In our work, we've integrated alternative futures analysis with spatially explicit and mechanistic models of the interactions and feedbacks between human activities and climate change impacts. Our intentions in coupling simulations of human decisions with those of biophysical processes are to explore the spatial and temporal relationships between people's actions and events in the landscape. While our case study is targeted to a specific suite of issues related to local climate change adaptation in the Willamette Valley ecoregion, the framework can be adapted to incorporate nearly any of the issues that other speakers have discussed in this conference and to any type of landscape. Modern ideas of alternative futures analysis originated with strategic planners and futurists in the 1950s through 70s, including Herman Kahn's development of scenario planning for the U.S. military through his work at the RAND Corporation, and Royal Dutch Shell's early use in business applications spurred in large part by concerns about Arab oil embargoes. Over time, an emerging group of futurists worked in both academic and applied realms. Their approaches have been characterized by an emphasis on alternatives, choices, broad-scale participation, long-term policy development, embracing system complexity, and working towards sustainability. In today's talk, I'll briefly outline the ways in which we've married these two approaches, alternative futures analysis and spatially and explicit simulations of landscape change, in the context of an agent-based model of human decisions, and present some of the results. The goal of our work, like that of much of alternative futures analysis, is to help people imagine the possible outcomes of alternative courses of action. In the process, we also aim to provide people with conceptual and pragmatic tools for making better decisions. Alternative futures analysis is considered is particularly useful in situations where the spatial extent and time frames that must be considered are outside the bounds of daily human experience, thus limiting people's ability to envision a large landscape in its entirety or to imagine change far enough into the future. It's also well suited to situations with high degrees of system complexity and uncertainty. This includes not just biophysical uncertainty, but the uncertainties of human social systems as well. When both these conditions are met, alternative futures analysis takes on special significance because plans are likely to be provisional, decisions ongoing, and the consequences of decisions can be expected to affect a broad spectrum of people with different backgrounds, goals, and capacities. In such cases, alternative futures analysis in conjunction with landscape change visualization tools could provide a means to bring together people from many different walks of life to develop common understandings of the choices they may face and to engage in meaningful dialogue about how to proceed. So what are scenarios? They're really what-if stories about the future. Scenarios are most useful when they're based on several key precepts, such as those noted here. The ones by Nancy Grimm are pretty straightforward, right? The ones by Stephen Carpenter put forth more nuanced points about the importance of marrying science and rigor with creativity and imagination, as well as strategic choices intended to maximize the usefulness of the set of scenarios as a whole. In our work, we received extensive guidance from several stakeholder advisory teams at different stages and for different purposes, principally and particularly during the development of the scenarios themselves. Overall, they're intended to make our work more relevant and more realistic. So what are the issues and uncertainties that can be used to frame our scenarios? We want to explore three scenario dimensions that bracket key uncertainties, choices, and leverage points: the intensity of climate change impacts, land use planning policies that control urban and rural growth, and as well as rural land uses, and wildfire risk protection. These are some projections of climate change, and particularly on the area burned in the future by MC1, a dynamic global vegetation model. Our decision in order to bracket a plausible range of variability was to use, for our low impact scenario, a Muroc A2 scenario, and for high impacts, a Hadley A2. You can see up here that in the Willamette Valley, very little apparent projected differences in the amount of fire burned in the future, whereas in here, the red indicates 400% or greater area burned within the next 100 years. For our development scenarios, we wanted to contrast compact versus dispersed development, essentially a continuation of Oregon's statewide land use planning system, which constrains urban growth to be in areas inside urban growth boundaries, versus more dispersed development patterns such as those in many other states, and which have become quite possible here in Oregon under a number of voter initiatives in recent years. And then the third dimension, looking at fire hazard treatments, we wanted to contrast ideas of conventional thin from below that remove small trees, brush, work on ground fuels without regard to species composition of the trees, versus restoring fire-adapted oak ecosystems, oak and prairie ecosystems. And we see a range of the types of scenarios that we developed here with our stakeholder guidance. And in particular, this latter contrast was motivated by our desire to test the degree to which biodiversity can perform an ecosystem service that protects human health and economic well-being. So this is the result in fully crossed scenarios of a 2-by-2 matrix of those choices. It allows us to statistically assess the effects of each individual scenario dimension at very simple, like analysis of variance, as well as to dig in deeply with much more nuanced methods such as structural equation models and more. In this case, then, we have our 3 dimensions, and each letter, the upper one indicates high climate change, compact development, conventional fuels management, versus the one below, low climate impacts, compact development, conventional fuels. If I look across this dimension now, I'm comparing the high compact conventional with a high compact mixed fuels diversity approach. We also added in 4 other scenarios that were about no management. They included implementation of defensible space around homes. They allowed people to manage timber, but they had no wildfire hazard management whatsoever to serve as a null model. We simulate each of those scenarios in our work now. We've used 50 times just because we cannot handle the data beyond that. If we fully expose the lines of data that are produced by this, we'd have 2.5 billion lines of data, which tends to crash my computer. But what we did then was with those 600 model runs, we're able to, each one represents a unique future that's been played forward 50 years in time at annual time steps, with human decisions, wildfire, succession occurring, urbanization occurring. And because of this, we can look not for sort of single solutions that point to a direction we should take, but rather to explore and test which types of policies may be robust against the variability and uncertainties that are portrayed in these scenarios. So a simpler way of saying that is this, and I stole this from somebody else, but we're not trying to predict the future. We're trying to explore and test policy sets that will be robust to future uncertainty and to help people make better decisions and think that through. So we're not doing a crystal ball. We are trying to do, however, make useful models. And I don't want it to be a complete black box because Phil told us not to give more than 1 or 2 method slides. So I'm not gonna, but I want you to understand there was a substantial process for 4 years where we looked at the relationships between our conceptual and theoretical frameworks, back and forth with a couple of model development, scenario development, model validation with the stakeholder advisory team, a very iterative process. This is an overview of the agent-based model and vision we used. If you want to ask me about it later, I'd be glad to describe it. But basically, we have actors who control individual areas of land. They are guided by actions they can choose in the land, which are called policies. They work within the landscape, and there are autonomous change processes. In this case, we have a climate-sensitive vegetation succession model and a mechanistic fire model, both being driven to large part by MC1, a dynamic global vegetation model. And sort of at each level, we have these types of complexities of interactions and feedbacks that are going on under the hood. This is what I want you to remember, though. It's the interactions and feedbacks between climate, vegetation change, wildfire, landowner decisions, policies, and landscape productions. I'm going to go through this pretty quickly. Our study area was located at the southern end of the Willamette Valley in a represented area of wildland-urban interface represented by the orange and yellow. It's 815 square kilometers, 16,000 tax lot parcels, and we divided it into 86,000 land units by intersecting tax lots with soil phase polygons. It's around the Eugene-Springfield metropolitan area. We populated each of those 86,000 polygons with an agent who was based on a survey of over 900 landowners in the Willamette Valley, the idea being that agents, like people, have values and that values affect their decisions. The temporal dynamics are, to me, one of the most fascinating parts about the model, in that, for instance, over time, we'd have to build a management scaffold. This shows the hectares of land that are in different forms of restoration or fire hazard management over time. The main point being that it takes about 25 years to build the management scaffolding that is supported by the budget, which is, in our landscape, $750,000 a year, not a small chunk of change, to maintain fire hazard and restoration treatments in the valley. There is also, on the lower part, an accumulation of areas that are unmanaged but have been previously managed, which has changed their fuels and other successional trajectories. What you're seeing here now is a quick simulation of 30 years of management applications. We're just isolating those fuels and restoration treatments. The red is principally the conventional thinnings. The other colors are oak restoration. And what you're seeing is it reaches equilibrium, but then it keeps changing. People are changing their minds. They're abandoning treatments. They're stopping them. New people are initiating it. So it's a very spatially dynamic model. If I look now at a mixed scenario, we begin to see the greens and browns of the oak restoration. Also notice there are fewer treatments in the mixed scenarios because those treatments cost more, but they have greater longevity, so they last over time. And then we begin to replicate it. You see the spatial variability that occur even within individual scenarios. The fire model is very dynamic. We spent a lot of time using FlamMap to develop a mechanistic fire model that has explicit fine-grained fire perimeters that will then interact with the fine-grained decisions that landowners are making. You see fire being driven in this model by wind, by topography, by the fuels in the ground, and by explicit climate weather that's being driven by the dynamic global vegetation model. If we play that out then in some simulations, we have a lot of capacity to control what goes on in the model. These are some outside simulations where we've located identical fires in different scenarios, from the no management to the conventional to the mixed. And you see not only very different fire sizes that come out. Note that the fires in the mixed scenario with grasslands are about the same size in many cases as those in the no management scenario, because grass fuels spread quickly, fire quickly. The conventional tends to reduce fire size, but it doesn't reduce fire intensity as much as the mixed scenario, the grassland fires do. I'd love to dwell on this slide, but I won't. There's fire intensity embedded. Basically, higher intensity fires and large area burns with no management, large areas burned at lower intensity in the mixed, and smaller areas burned but moderate intensity in the other scenarios. This is the WUI. This is the wildland-urban interface going under our urban growth model. You see they bracket scenarios where as few as 5% of the doubling of population in the Eugene-Springfield area is projected to go in rural areas, to those where up to 35% of new residents go there. The model then, here's where you put it all together. There's vegetation on the upper right there. Greens are forest, reds and yellows are savanna and prairie, browns are ag, dwelling units in the lower right. Big fire comes through in this case. Houses are exposed to fire. Note that most of the stand replacing fire in black is not where the management treatments are. And when the fire is replaced later with vegetation, those stand replacing hours, that pink, are some of the new vegetation types that are emerging under climate change. It's a very dynamic model over time. These are the same scenario showing amount of area burned over 50 years. Note that the amount of area burned is different than the amount of homes that are threatened. You have there in the orange a small fire with a lot of threatened homes versus a large fire with very few threatened homes. Get into some of the quick results that we've had. It's really clear in our model that fire is an enormous driver of this. The area burned in decade under the high climate scenario dwarfs that on the right of the low climate scenarios. The low climate scenario doesn't show much more fire than the historical record. It increases principally due to population growth, because in the model, fire growth, changes in wildfire are driven by climate, they're driven by fuels management, and by population growth and increases in ignitions. The number of threatened residences also rises dramatically with climate change, but not proportionally as high as the amount of fire because of the success of the treatments. We look here, there's two things that are of note. As I described before, these are periods over time. These are decades in the model. Is that there are similar amounts of area burned in the mixed and no managed scenarios, less in the conventional, but that the threatened residents are relatively similar in the conventional and mixed, though slightly higher in the mixed, and I'll get to that in a moment. So we do a lot of time then. We're beginning to partition risk in space and time. Without going into the details of the slide, what we're seeing is that under the conventional and mixed scenarios, in the areas of the landscape that are treated, you have very low threatened residences, relatively small amounts of fire. The no management scenarios are sort of going off the roof here. But what happens is that If you want to live in this landscape, you'd like to live in an oak savanna because it's very easy to defend your home, fire intensity is very low, but what happens is the mixed fires in our model spread fire substantially to hit that other 60% of the landscape in which there is no treatment, and it creates safe zones and danger zones. Is this real? I don't know, but it points out the types of things we can have great discussions about with our stakeholders. The summary points is that large uncertainty in future climate creates challenges for fuels management. We could be investing in the future large amounts in conventional thinnings and get very few benefits if climate change doesn't manifest to any great extent. On the other hand, if we incorporate both the biodiversity approach to this, we have benefits regardless of whether climate change manifests according to the higher climate change impacts. But with some caveats about dangers that may have to be taken under control. Acknowledge a whole bunch of people. The data sets are available and the results are available online.